Hi. Hi. Hello, hello, hello. Okay, hi and hello. And hi. Oh, I like the enthusiasm is growing, or at least from in one direction. So hi, Maisha. Hi, May. Hello, Eric. Hi, Lizzie. What? Wait. Oh, congratulations, Maisha. I believe I could never guess. I have no idea who you're talking about, but that's good. Right. No, no, I totally get it. No, that's great. And wow. And I should open up a class participation portal for people that have the uh, enthusiasm and self-confidence to share their good news with the group. That is tricky for some of us to be able to do. So that's great. Hello, Elizabeth with an S. No, that's great. Yeah. Oh, how did she do that? How did Elizabeth just join and understand what Maisha was saying? That's okay. No, that is very, very exciting. And wow, look how nice your classmates are for like, really, thank you, Lizzie, and thank you, Elizabeth, for being so supportive of your classmate. And thank you, May. Look at that. I mean, this warms the cockles of my heart, even though I totally do not understand what cockles are. No, yeah, that is very, and okay, I'm going to pause for a second. That's so nice of all of you. Like, I mean, in certain circles, in certain social circles, like if someone actually had the guts to share good news, other people would get all curmudgeonly and competitive and this and that. And maybe that is what they people anyway. I think it's cool. That's cool. That's very cool all around. And I'll also use that as a and I really do. And I think it's cool that Maisha got what she deserved, so to speak, in the good sense, and that she felt comfortable sharing it, and that you guys are so supportive of her, and that I'm sure it would go in the other direction, that she would be supportive of you when you have your good news, and feel free to share it here because what the heck. And yes, on the subject of like ambitions and accomplishments and good news and stuff, let me remind you all again what something I said last semester. I still think COVID is very hard. I still think life is very hard for all of you and for me. And I think the fact that you're still hanging on and doing schoolwork and doing school and like trying to get jobs, like fighting for your future, I still think you get major points for that on all of you. I mean, the fact you're surviving this madness at all, and I don't think the madness is over. In fact, every single time someone declares that the madness is over, that it gets even crazier and worse. I am glad that the mask thing is optional now. I think that's terrific. But all I'm just trying to say is I think the fact that you're all still in school at all is remarkable. The fact that you're still doing hard things at school is remarkable. I'm also saying this from personal experience. I have two children. The older one is definitely not still in school for whatever it's worth. I shouldn't be saying this on YouTube, but like, I mean, it is rough. I mean, it is rough, and you guys are doing very well. And again, also as things emerge and as things, I didn't say he wasn't in school. I didn't mean that. That wasn't quite right. But it's a struggle. Anyway, and I meant it metaphorically. But as things unfold and as you pursue more things, do please feel free to reach out and use me as a resource to support your aspirations. For example, letters of recommendation and all of that. Yes. Okay. So we've covered this, but no, I'm happy that things are still going well for you guys in these crazy times. Okay. And I'm happy that once again, I saw at least one person yesterday who shall remain Lizzie-less or nameless. And that's cool that I'm getting to see you guys in real life occasionally. That is very cool. Okay. No, and thank you. Seriously. Okay. Okay. So we should get to physics now. So physics. Excuse me. Oh, yes, May. Absolutely. All right.
I'm gonna just say it out loud.
Good.
What's happening this Friday for lab? Because we haven't heard anything about this week, Friday.
Oh, sorry. Oh, I thought okay. No, that's a very fair question. And also, by the way, I don't know if you noticed, but there's totally a portal for points for the fact that you just used your voice, which I really appreciate. You could totally submit that for points in a participation portal. But yeah, and I'm sorry. Yes, no, lab is back totally, or should be, unless you heard something different. Let me back up. Lab should be totally normal and on and in person, and with Professor Walters, it should be back regular this Friday, unless I know we didn't have it last week, and I did make that announcement, and I can explain why, and I apologize. That is true. And I know things have been very rocky and weird this semester, but unless you, well, let me back up and ask. You're asking just because you just like literally don't know, because you haven't heard anything, and because things have been so weird that you're asking because you haven't heard anything, not because you actually heard something confusing. Is that correct?
Yeah.
Okay, fair enough. Yes. So to everybody, and I should put this in Google Classroom or in the chat or something. Yes, like things have finally settled down, and you should be in the lab for real this Friday with Professor H. Walters. We did have a whole situation last week that affected all the labs differently, but I canceled all the labs last week. Yes, but that was last week. And yes, we've been not having certain like some of the lab sections didn't even have an instructor at all until this week. So that was chaotic. And yes, Professor H. Walters was away for 2 weeks at the beginning. So blah, blah, blah. But yes, yeah, I'm glad May asked, because I know this has been all a nightmare. Well, hopefully not a nightmare, but it certainly has been very confusing. So this is the first week that finally all of our dust is settled, like all of our new lab instructors are hired, all of our family issues in other countries that have been happening, I think have settled. So unless I hear otherwise, or unless one of you tells me otherwise, we should be back to normal in the lab this Friday with Professor H. Walters. But that's a very fair question. But does that answer make sense? We good? Does that answer?
Yeah, it does.
Okay, cool. Thank you. And please submit. I'm so glad to hear your voice. That's great, because I haven't met you yet in person. So that's so anyway. Okay. Anyway, blah blah blah. Okay. Cool. Yes. You know. Well, yeah. Okay. No. Okay. I'm just. Yeah. It's been a. Okay. Another thing, just to. It has been a chaotic semester. I shouldn't use these strong words like chaotic. It's been a confusing, jostly semester, especially with regard to the lab. And I take response. That is ultimately me. Ultimately, all issues of that kind land on me or come from me. And I apologize to all of you. One thing, and I don't mean this as a defense, but just as a reminder, is this is our first semester being back on campus at all as physics program. I know there are other science classes had gotten back on campus last semester. Okay, I'm going to look in the chat in 1 second. I know that other science classes had gotten back, into their labs and into their physical classrooms last semester, if not earlier. But we had been fully online until this semester. So we're definitely suffering a lot of transition challenges. I say suffering, like, no one's doing them to us, but it's just funny. Maybe I mentioned this to you guys before, but like, we got back in the lab officially, and I've been in the lab physically myself and stuff, but I could not believe, like, dusting off lab manuals and things like that. It's just so weird. We've been out of it for so long. Like, it's like another world in my mind now. So we're definitely having to reinvent certain wheels and processes, and we had to hire new people and blah, blah. So that's probably every time I say COVID is not over, I'm probably partly thinking of things like that. But okay, wait, chat. And we will start doing physics now. Oh, that's so nice. And I thought it was a direct chat too. Oh, wow. Okay. You guys are too kind. Well, thank you. I appreciate it. I don't know what to say. I'll take it. Good. That's good. Oh yeah, okay. Speaking of yay. Oh, now she's okay. Now someone wants to kill Maisha for sure. She's saying yay. Okay, but thank you for reminding me, Maisha. Yay. And that's a funny thing to say right after, like, oh, physics doesn't have stress. Oh, there's new homework. Okay, yes, it is true. Just to be clear. Yes, I still excuse me, I don't know. This class gets me so worked up. Oh my goodness. It is true that I still owe you things back. I mean, I caught up on a lot of those game turns, and I hope people notice, like, if you did submit to any of the game portals for extra points, those did, video or avatar or YouTube, like a lot of those came back. I mean, I finally caught up with all that stuff this weekend, and that's good. So please do them. Like, they don't go nowhere. They do actually count. But I still have to get you back your homework 1 and stuff. It's ridiculous. It's mortifying at this point. But yes, indeed, we finally moved on to newer material. So you'll notice that, yes, I did post a homework 2 that's due a week from this Monday. I want to say a couple of quick things about it. And then I also went ahead and posted homework 3, just so we do, so we can make some tracks. But the homework 3 is due the following Monday. And frankly, by the time you get to homework 3, I think many of you will find by the time you do homework 3, I think that many of you will find it to be somewhat practice exercisey. Let's back up and recognize homework 1, which we've been on forever. I asked you to think through and figure out all of these things way before we ever talked about them, for good or for bad, and then we ended up talking about them for a month. There were all these topics that you had to think through to the extent possible on your own. And then we went through them all. Homework, for what it's worth, homework 3 is not like that. Homework 3 is, now that we've been talking about this for a month, can you do a practice exercise on this and sort of help yourself for the exam? So that's due in 2 weeks. It's not even due this Monday. Some of you might even, you might take a look at it. You might even want to do it first. It's not that long is what I'm saying, that homework 3. Now, homework 2, the one that is technically due this Monday, let me make a comment or two about it. And again, I still have to get you back stuff, and I apologize, but just stay at whatever pace you're staying at. But homework 2 is called Math Methods. It is about, it's really about these underlying math tools that we kind of need for this class, many of which are calculus kind of tools, some of which are trigonometry kind of tools. Math Methods is there to help you review or practice or exercise these mathy things that we need. Some of you, again, it'll be a helpful refresher to see where you're at. Some of you, it'll just be practice. We'll see. But it's a little bit long, that Math Methods packet. It's a little bit long. It's a little bit repetitive at times because it is for practice. But I'll just warn you of one thing. Like, first, it does a bunch of these derivative ideas that we've been doing in class. And then it does some trigonometry ideas that we're about to be doing in class. But the very last piece of the whole thing is about vector multiplication. That is something we do need for the class ultimately, but we don't literally need it right now. I mean, it's helpful. But if you have to make a choice and by next Monday and do everything, but you don't get to that, it's okay. I mean, I kind of try to always say this, but I explicitly mean, if you handed in the whole Math Methods thing and save the vector multiplication for later, because you're triaging, fine. You'll just hand it in later. But you could do it. You could do it based on everything that's written in the sheet, but it's the last priority for right now. Okay. So, so now I'm going to, okay. Oh, wait. Okay. So I'm looking at the chat now. So we're going to, oh, this is interesting. Okay. Wait. So I am going to, I promise I'm about to get to physics here, sort of, whatever that means, but I'm looking in the chat. Wait a minute. First, I'm looking at, so Xiaowei's question, what is a cosine? That's a good question. I mean, in a way, I'm about to talk about that on the next page and stuff. But wait, I think I even say it on the next page. Hang on. I really do want to take Xiaowei's question seriously before I go to the other things in the chat. Well, one quick answer, Xiaowei, is A is just another letter that means the same thing as why not. Like, sometimes we write why not, or sometimes we'll say like x equals x naught cosine blah blah blah. But we could just as easily use the letter A. It's just another letter that means constant, that means initial displacement from equilibrium. A, capital A, happens to be the letter that I think tends to come up in the lab, like in lab 3. And I should ask you where you are in the labs right now. I mean, I think you're up to lab 3 with Professor Walters, but let me turn the, and by the way, also, let me say the equations that are in the middle of the page right here and now are things that I want to explain. Like that's my goal for today. They should look sort of familiar. Okay, so I'm talking to Xiaowei, but I'm talking to everybody. Well, this is sort of the point of my lecture today. I mean, she's like a step ahead of me in a way. But partly what I want to get at with all of you is we're developing this math that's underneath the physics. We're developing these differential equations, how to recognize them, how to get the solution to them. But the kind of one of the big lessons of the math to everybody is we want to get in the habit of not getting overly concerned whether we see the letter X or we see the letter Y or something. Like, we want to know that everything I'm doing with math about X could just as easily be done about Y, as long as X and Y both mean dependent variable. Like, in other words, and I'm going to say this on the next couple of pages, in other words, some of you might be noticing that you keep getting equations that look very similar, but they sometimes look a little bit different. And sometimes that can be confusing to people. Like you might be noticing sometimes I'm saying X equals X naught cosine omega t. Other times I'm saying Y equals Y naught cosine omega t. Or then still other times, like right now, I might say Y equals A cosine omega t. That can, and in the lab, they might say it slightly even differently. That can be jostling and annoying, but we're not doing it to jostle or annoy you. We're doing it because we really want to get used to the fact that all those that different letters are used for the same thing. And the important thing is not what letter it is, but whether it's a dependent variable or an independent variable or a universal constant or a parameter constant. So I'm going to explain a little bit more in the next page or two, but and if you're seeing an extra Greek letter in the parentheses there in the middle of the page, then don't worry, I haven't explained that yet. That's what I'm going to explain today. So I'm not trying to confuse anybody, but my short answer to Xiaowei's question is that A means the same thing as Y naught, and Y naught means the same thing that X naught would mean if it were an X equation. I don't know if that helps or not. And you can tell me privately or publicly, Xiaowei, if that did answer your question. But it was a good question. And I will say more about it. But now let me see the rest of this chat. Hold on. Okay, yeah, that's what I thought. Yeah. So the chat between Maisha and Lizzie, this is good too. And again, both of you, both of you can submit for the multiplayer co-op and the closing of conversational pathing, because you're both like having a dialogue. Very helpful. And I agree with what both of you, and yes, like to all of you, like MSRC has gone through a lot of ebbs and flows through the years. Like, it changes. Some years it's an incredibly useful resource, and some years it's less, or one blah, blah, blah. But my ultimate thing is to all of you, you should use any resource you want in every context possible, except maybe sometimes sort of exams. Like, yeah, and I agree with Lizzie, and I do know that Lizzie's right that MSRC has these rules about exactly how helpful they're being or not. I shouldn't say that. They have rules to stop them from actually cheating for you and to just help you. I mean, Lizzie's right that they have those rules. It's also true that some years they break those rules. But the truth is, if you guys are asking me, I don't even care about all those rules and stuff. When it comes to homework, you do whatever you need to do to get yourself to understand these things, and I will give you credit for it. And there is and you know in your heart, I mean, the standard is, and the standard on exams is, just don't write something down that you don't understand. That's my ultimate thing, is do whatever you want to get the understanding, talk to anybody, any tutor, any web service. But by the time you actually write it down, make sure that what you're writing down, wherever you got it from, you do actually understand. And to all of you, let me say two things about that. That's even true on exams. To me, I don't care about giving credit to where you got things from. This is physics. Like, none of us made this up. And none of us is claiming to make this up. It's not a matter of like footnoting and stuff. But to all of you, my standard, it's not that I don't think that cheating is a thing. Cheating is possible. People do it, and it is bad. I just have a very different definition of cheating from what maybe a lot of other people have, maybe. My definition of cheating is writing something down that we know in our hearts we don't understand. That's my definition of cheating. And the real important question is, well, is that a kind of definition that Yavrabam can enforce? Like, if I write something down on the exams that's correct, but I don't understand it, like, can he possibly know that? And the answer is yes and no. The answer is, I promise you this, there's a ton of cases where you think you're writing things down and you know you don't understand them, and you think, but you know they're right, and you know they're detailed, and you know you got them from a good source like on the web, and you know that everything you're writing is correct, but you just don't understand it. And you think in your mind, well, how does he know what's in my mind? And let me tell you, in many, many cases, I totally do. I just do. I mean, just in the way that if you speak another language at home in your house, like Spanish or Chinese or Arabic or something, and I attempted to like say something in Arabic or Chinese or Spanish by like reading off a script or by copying something, that like, I don't speak, I mean, I do speak Spanish actually, sort of, but like if I attempted to write out something in Chinese or say something in Chinese to your family, if you all speak Chinese for real, right? And I attempted by copying something to write down something in Chinese or say it in Chinese so that I could get away with like fitting into your family, you all would know that I didn't understand a word I was talking about, right? You would just know. If I don't literally speak Chinese, and I don't literally read or write Chinese, and I try to copy the characters and then hand it to you and say, this is like, whatever, this is what I did for my summer vacation, you just know the language enough to know that I don't know the language, and you would know the difference, right? Like, you know, if I tried to fake Chinese, you'd know I was faking it. Even if I literally spent hours copying all the characters, I just don't understand how those characters fit together. I don't know what it means to make a sentence in Chinese. So even if I imitated all the sounds or all the symbols, it just would not be Chinese, and you would know it. Or similarly, like if I went over to the piano and like tried to plunk out notes of like some like concerto that you actually know how to play, you'd know that I don't know how to play piano, right? So on the one hand, I don't know why I'm getting off on this because this is what I do, but on the one hand, the only standard I have for cheating is don't write crap that you don't understand. Get the understanding any way you want, including an MSRC tutor, including even Chegg, I suppose. If you get the understanding, get it the way you want. By the time you write it down, only write down things that you understand. And on the one end, know that 9 times out of 10, oh, I do know the difference. Believe me. Now, 1 time out of 10, I either totally don't, or I don't care because I don't have time, because your cheating is your business and I've got my own God to answer to, or my own quark to answer to, or whatever. So 1 time out of 10, you'll get away with it or whatever, or I've already given up on you because you're such a cheater that it's just not my problem, whatever. And then that's between you and you, and I'm just not going to, but we know what cheating is. Cheating is writing stuff that we don't understand. If we go to the tutors at the MSRC or wherever, and they guide our hand and they re-explain everything and they help us with the actual homework that was actually assigned, and we now get it and we return it in 4 points, quark, bless America. Great. That means you just got your money's worth, and we both did. That's totally fine as far as I'm concerned. Okay, I'm talking way too much. Okay. Oh, and it is lab 3. Good. Oh yeah, wait. So back to Jiawei. So really good question, and I'm gonna start explaining this now. But Jiawei's question, it's not so a cos. It's not a cos. It's not like a function a cos. It's just the letter a times cos, as opposed to like the letter x naught times cos. A is a capital. It means a number of meters. It means the initial. But I'll explain that right now. I see your question, but it's not arc cos or inverse cos or something. It's just the letter A times cosine. And the letter A stands for some initial value of Y. I'm using the same language that I think you do use in lab 3. But here, let me try to, but okay, let me get to the physics now. And I think maybe it'll answer Jiawei's question and other people's. Okay, yeah, so I'm going to do another little like sort of, forgive me, but I'm going to like a little bit review where I think we are now, because As Maisha pointed out, oh. Yeah, yes, Jiawei, yes, sorry, yes. Hold on, good, very good. And that counts as closing a conversation or a path, so thank you. That's points right there, Jiawei, but yes, let me put it in. Yeah, multiply, yes. Okay. So we spent all this time on homework 1, like what, and then a couple labs. What are we really saying? Like, what's our point so far? Here's our point. Like in the beginning of homework 1, we were specifically talking about a specific block of material, of mass, going back and forth on a coiled piece of metal known as a spring. And it was going back and forth along various positions of a meter stick known as the x-axis. And we were measuring its position on the x-axis back and forth. And we came to a bunch of conclusions about x and this equation, d2x dt squared equals negative k over m x, and all this. Now I want to back up and say, okay, all this math, all this time that we spent on the x variable as a description of the mass on the spring, all this time that we spent, we were really studying any system at all that behaves like a mass on a spring. Like the mass on the spring is the central example of this larger phenomenon known as simple harmonic oscillation. Okay, and simple harmonic oscillation could apply to a mass going back and forth on an x-axis, or it could apply to a pendulum bob going back and forth along a theta angular displacement like arc, right? Or it could apply as it will in homework 3 to a weather system whose temperature you're measuring throughout time and whose temperature you notice going up and down and up and down and up and down in time. Okay, I'm saying from here on, all the math we did applies. The math doesn't know what physical system we were looking at. The math is just treating a relationship between variable quantities. So I'm going to generalize our conclusion that we got from the math and the physics. I'm going to say from now on, so I'm reading the sheet here. From now on, if z, lowercase z, stands for any possible measurable dependent variable, right? Like z could be position along an axis, or it could be position along a different axis, or it could be angular position along an arc, or it could be temperature, or it could be electrostatic field magnitude, whatever. Z is some quantity that you measure and a quantity that seems to be varying somehow in time, right? So what we're saying is then, if we have reason to believe that this differential equation, d2z dt squared equals negative omega squared z, if we have reason to believe that that differential equation describes what z is doing in time, then we know right away z is oscillating harmonically in time. Like z might not even be a physical picturable item. It might be literally just the value of a measurement. Z might be a number. But if that differential equation applies to the number z, then z is going up, and then the value of z is going up and down harmonically in time. Now, what does harmonically mean? Well, I'm going to say on the next page, I guess, but harmonically means not just going back and forth or up and down or whatever. Harmonic oscillation is a very special, very steady, very regular, predictable, rhythmic, constant type of oscillation. And any system that's describable by that differential equation is a system that is oscillating in this harmonic way. To actually oscillate harmonically means the following. To oscillate harmonically means, number one, to oscillate constantly. And what do I mean by constantly? So I'm looking in the middle of the page here at A. If you're oscillating harmonically, it means you're doing something cyclical, something periodic, something over and over again. And it means the rate at which you're cycling is a constant. Okay, that's point number one. And there's three different ways to describe that constant rate at which the system are cycling. You can describe it with omega, you could describe it with F, or you could describe it with capital T. Now, each of these three things ultimately describes the same idea, which is cycling rate. These are three distinct ways to think about or to describe rate of cycling. They're interchangeable in the sense that if you know one, you automatically know the other two. And that's very important. Like, they are equivalent that way. In truth, we only need at any given moment one way to describe the cycling rate of something. If you know the omega, you automatically can figure out the F and the T. If you know the F, you can figure out the omega and the T, vice versa. They're all interrelated. The reason we have three different ways to describe cycling rate is that one, omega, is the most directly mathematically useful, convenient, clear. Omega comes straight out of the math. Omega is the most mathematically direct and the most mathematically useful way to describe the cycling rate of an oscillator. Omega means angular frequency. So it's a measurement of cycling rate in radians per second. It's the most mathematically useful. However, to all of us, because it's mathematically direct, that means it's the least connected to what we're physically picturing on our mind, or what we could physically relate to, or what we could like measure in the lab. Like, if you think that omega is kind of abstract, you're correct. It is kind of abstract in the way that math is abstract. It's super mathematically useful, but it is a little bit hard to picture. What radians per second, what angular frequency is it's measuring the rate at which something cycles, but it's measuring it in radians per second. What do radians have anything to do with anything? Remember from Monday, please, ultimately, a radian is a sixth of a cycle. Okay, that's really, in my mind, as a physicist, that is the best way, when in doubt, to just picture a radian or think of a radian. I mean, it's approximately a sixth of a cycle. Why? Where did I get that? Why am I saying a sixth of a cycle? What I'm really saying is what a radian is the size of a certain angle. And an angle is a fraction of a circle. And circles are what we're using to picture cycles as physicists. There are 2 pi radians per every circle/cycle, right? Like, that's the memorizer, if anything. And that is strictly true. That's not approximate. That's literally true. Just like there are 360 degrees to a circle, there are 2 pi radians to a circle. If you say, okay, yeah, I get that there's 360 degrees to a circle, like, fine, like a degree is just like a 360th of a circle. And by the way, that is all a degree is, right? Please remember, an angle is just a fraction of a circle. Like a right angle is a quarter of a circle. A 180-degree angle, or whatever you call it, is a half of a circle. Angles are just fractions of circles. And they're literally fractions in the sense that they don't care how big or how small the circle is. A right angle is a right angle. Like, whether I do like this or I do this, it doesn't matter how big the circle is. It's just a quarter of a circle, right? So what's a degree? A degree is the thing that we use when we decide to divide circles into 360 small fractions, small parts. A degree is literally just a 360th of a circle, right? That's all a degree is. What's a radian? A radian is the thing that we do. A radian is, let me put it the other way. So a circle can be divided into 360 degrees, or you can divide a circle into 2 pi radians. What's 2 pi? It's a little bit more than 6. I mean, because pi is a little bit more than 3. 2 pi is a little bit more than 6. When we say that we divide the circle into 2 pi radians, you might say, yeah, but okay, I get that there's 2 pi radians in a circle, but like, what is a radian? No, a radian is just that. A radian is that piece of a circle that is that big. That's all that a radian is. Just like a degree is a 3/60th of a circle, a radian is a 1/2 of a circle, which is approximately, if you're just trying to picture it, just get a sense, that's basically a 1/6 of a circle. It's just a little bit less than 60 degrees. Okay, if you were to divide a circle into essentially 6 equal parts, each one of those parts, which is a little bit less than 60 degrees, would be a radian. That's all that a radian is. Okay. So when we say that something is oscillating at, if I say this thing is oscillating at an angular frequency of 4 pi radians per second, I know that sounds like nonsense. Believe me, even to me, that still sounds like nonsense. If someone walks up, if I'm looking at something going back and forth, I'm like, oh my God, look how fast that thing is going. It's going. How fast is that thing going? If you turn to me and go, oh, it's going faster. Oh yeah, you're right. It's super fast. It's got an angular frequency of 4 pi radians per second. Of course, my brain first goes 4 pi radians per second. Okay, first of all, pi, like what? Second of all, radians, like radian. And then I'm like, oh yeah, radians, something to do with angles, degrees, circles. And then I look at it and I'm like, what are you talking about? The thing's just going back and forth and back and forth. I don't see no circles. I don't see no angles. I don't see no pi. Like what? I just want to know how fast the thing is going back and forth, back and forth. And you say 4 pi radians per second. But what I'm saying is, whoa, 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 just to everybody calm down. By everybody, I mean me. But I'm saying, no, 4 pi radians per second. It actually does make sense. If you do, right, great. Exact. So to Elizabeth's question, I don't know if she's like literally asking me or asking the class, but yeah, that's exactly the right question. And totally, please put that in for participation, Elizabeth with an S. If I say 4, so, and then tell me, I'm about to say what I think the answer is to your question, because I think you're asking me, but tell me if this makes sense, because you're right there with me. You're exactly thinking about the right thing. If someone says 4 pi radians per second, what that is 2 cycles per second. That's what that means. That's all that means. And to everybody, where I get that, they say 4 pi radians per second. And in my mind, I go, oh, cool. All right. Thank you. All right. Sweet. And definitely put that in. I feel like, okay, so at least one person's with me. That's right. And I'm still going to say it's one more time for everybody. But yes, what I'm saying, and you can literally, this is an equation that I think I put in the notes yesterday or on the board, but definitely like it's just a conversion factor. What I'm literally saying is that F equals omega over 2 pi, or if you like, omega equals 2 pi F. I mean, if you want it, it's right. I'm saying there's 2 pi radians per every cycle. So if someone tells me 4 pi radians per second, I just literally divide by 2 pi in my mind. I'm like, oh yeah, 4 pi radians. Well, 2 pi radians would be a full cycle. So 4 pi radians is 2 cycles. So what they're telling me, if they say 4 pi radians per second, they're just saying 2 cycles per second. And they're saying cycles, meaning there and back, right? See, so what I'm trying to tell everybody, but I'm glad Elizabeth gets it, like seriously. And I know she's not the only one. I appreciate that she like stepped up. What I'm trying to tell everybody, because this confused me forever, like we're trying to describe systems that just go back and forth, back and forth. There may not be any curve or any angle or any circle in the system that we're looking at. It might just be going back and forth. But because it's cycling, we have all of this mathematics that come from circles because we're using the mathematics of circles to describe cycles. So when we say radians, it makes us picture things like angles and circles and stuff. I just want to drum into everybody. A radian is just a 1/6, a 2 pi. It's approximately a 1/6 of a cycle. That's what it is. So if someone says 4 pi radians per second, what they really mean is 2 cycles per second is standard frequency F. And then I'm going to say, and I think I put this in the notes yesterday, stop me if I didn't, but if I say to you 4 pi radians per second is omega, then the first thing you could say in your mind is, okay, so the standard frequency F is 2 cycles per second. Then you could say to yourself, and please do put this in your notes if I didn't already, if I'm not, when you say to yourself 2 cycles per second is standard frequency F, then you can say, and oh yes, in life, in the world, 1 cycle per second is called a hertz. So then you say to yourself, oh, so you go, oh, 4 pi radians per second, that's really 2 cycles per second. Oh, that's a frequency of 2 hertz. With me so far? And hertz, like as in if anybody still listens to the radio, I don't know if any of you do, but like if you ever listen to like the radio, it's like 90, like NPR, WNYC is 93.9 FM. Excuse me. They say WNYC is 93.9 megahertz on your FM dial. Again, I don't know if anybody can relate to this. I don't know if anybody listens to the radio anymore, but if you do, that's the kind of thing they say. 93, they'll say 93.9 megahertz on your FM dial. Megahertz means millions of hertz. A hertz is a cycle per second. When they say 93.9 megahertz, they're saying that something, an electromagnetic wave, is vibrating, is oscillating back and forth at a frequency, a standard frequency of 93.9 million cycles per second. Okay, that's what that means. And FM, by the way, stands for frequency modulation. Modulation is to change, to adjust. So FM stands for frequency adjustment. And the frequency of a particular radio station is how quickly it cycles something, electromagnetic radiation, cycles, and we'll get to that by the end of the class. That's like the point of the class. Gets back and forth, back and forth, back and forth, that many cycles per second. Last thing I'm going to say now, and I know I'm sort of all over the place, but I'm right in the middle of the sheet, is once you know that something is cycling at 2 cycles per second, 2 hertz, then you could say to yourself, oh, if it's doing 2 cycles every second, then that means it's taking 1/2 second to do every cycle, right? I literally just flipped it. I'm saying, and again, I think I put this in the notes yesterday, but I'm saying like period amount of time for 1 cycle is just the inverse, the multiplicative inverse, the reciprocal of standard frequency. If you do 3 cycles in a second, then you're taking, if you do 3 cycles in a second, then you're taking 1/3 of a second to do a cycle, and vice versa, right? So ultimately what I'm saying right here, and I'm going to go back to the other page shortly-ish, what I'm saying right here is there's 3 different ways to describe cycling rate. You can describe it by angular frequency, omega, or standard frequency, F. Let me say that again. You could measure by angular frequency, omega, which is measured in radians per second, or you can measure it in standard frequency, F, which is in cycles per second, or you can measure a cycling rate in period, which is seconds per cycle. If you know one of these, you automatically know the other 2, or you automatically can get the other 2. We, literally speaking, at any given moment, we only need one of these descriptions. They are 3 equivalent descriptions for the same thing. But the reason we have all 3 is that omega comes directly out of the math. Omega is the most directly useful thing to use in the math of cosines and all of that. But period T is the most directly measurable in the lab and the most easily pictured by all of us in our minds. So T is the one we like to picture and sort of think in, all of us. Omega is the one that the math thinks in, and F, standard frequency, is like the bridge between the 2. Okay, so it's a matter of what context we're in. But okay, I'm just gonna try. I think I'm up to the end of the chat. Okay, cool. Okay, no, that was great. Elizabeth with an S. And so what? So that technically was just like a little review or explanation of what omega means. And again, I know omega takes a big role in lab 3 and possibly lab 4, but that's what omega means. It's a cycling rate, but it's measured in 1/6 of a cycle rather than full cycles. Now, if something oscillates harmonically, like anything can oscillate. Oscillate just means go back and forth, up and down, whatever. But if something's oscillating harmonically, first of all, that's only going to be true if it's describable by that differential equation that I wrote on the first page. But second of all, if it's oscillating harmonically, that means it's got a cycling rate omega ft that is so constant that it's not just constant, it's constant. That's already interesting. Like it won't change. But not only won't it change even if we play with the amplitude. This is a part B on the sheet that I'm looking at right now. I mean, on the notes that I'm looking at right now. I'm saying a definitive characteristic of harmonic oscillation is oscillation that is constant in time, regardless of configuration in space. Now, this is a big deal. This is interesting. What I'm saying, that omega can be figured out. I'm saying, I'm going to go back. I'm saying that if we have a harmonic oscillator, if we have that differential equation up there describing some variable like z, then we know that z is oscillating harmonically. And to oscillate harmonically means that z can be described with this cosine function like z naught cosine omega t. And the omega, the angular frequency, the rate of cycling that's fixed into the cosine expression, that omega is just necessarily and automatically the square root of whatever constant of proportionality we find in the differential equation. That's a little bit of a mouthful, but I'm saying the reason that I have an omega squared up there in the differential equation is to make this point. Omega squared just stands for some constant number. Like in the case of the mass on the spring, we had d2x dt squared equals negative parentheses k over m x, right? K over m was the constant in that parentheses. It was constant. In some other case, like a pendulum, it might not be k over n. It might be something like lowercase g over L. It might be like gravitational constant over length of string, like for the case of pendulum. In some other thing like temperature, it might be something else. In the case of electric field, it might be something else. Like I'm trying to say that the differential equation has this format regardless of what the particular details are. The particular details of the constant inside the parentheses might differ from system to system. But if it's a harmonic oscillator, whatever is in that parentheses is some kind of constant. Could be k over m, could be g over L, could be the number 25. It's just some constant number. And what I'm saying, the sort of tricky part that I'm saying is, whatever that constant is, for all time now, we're going to call that constant omega squared. We're just calling the whole number, the whole constant, omega squared. We could call it whatever we want. We could call it C for constant. We could call it beta. And we didn't have to call it anything squared, but we're actually calling it omega squared. And that's a little bit confusing to people. I'm not saying that we're squaring a variable. I'm not saying that this is a quadratic equation or a parabola or anything like that. I'm just like, I'm not squaring the z. Notice the z is not squared. The omega is squared, just meaning that the constant number in there, we're giving a name and we're calling it omega squared. Now, why? Why would we give it that confusing name if we're just saying it's just some number and we're just calling it omega squared? Because what we're really saying is, with the benefit of hindsight, with having done all this math already, what we're saying is whatever that number is, that constant, the harmonic oscillation will occur at a rate that is literally and directly and exactly the square root of that number. So we're calling that number omega squared in anticipation. We're really saying, like, we could have called it omega and then we could have put in parentheses down here square root of omega if we want, but that's like really clunky. I'm saying that omega, the cycling rate of an oscillator, is always necessarily the square root of whatever the constant of proportionality is in the differential equation. That is a mouthful. Let me just say it one more time. It's like a really, really simple but powerful idea once you get it, but it's like very weird until you get it. I'm saying, basically I'm saying this. I think I said this once yesterday, but I'll just say it again just to make absolutely sure. I'm saying, I think I said this to you, not yesterday, but Monday. Just making up a new letter that we've never used before. Okay. Okay, this is an example. I'm saying this quickly, and again, you'll know you get what I'm saying once you're like, oh, is that all he's saying? That's not a big deal. Then you'll know you get it. But I'm saying, if I just walk up to you from the forest and I'm saying, oh, we're measuring this variable P, we're measuring this dependent variable P. I don't know, maybe it stands for pressure in some gas, right? Whatever it is, we're measuring P. And I'm like, oh my God, it turns out that P can be described by this differential equation, d2P dt squared equals negative 36P, right? If I say that, then you automatically know, if that's true, if P can be described by this differential equation where the second time derivative of P equals negative times some constant times P itself, then what you automatically know is you're like, oh, well, then I guess P is oscillating harmonically. I guess the value of P is going up and down and up and down, up and down, just like a mass on a spring at a certain rate that you'll know right away. You'll know right away. I'm saying automatically the rate, the angular frequency at which something oscillates is automatically the square root of whatever constant we found in there. Why? Because when you differentiate twice and use the chain rule twice, like when you differentiate once, this constant, like when you take the derivative of this, you'll get negative P naught sine 6t. Sorry, when you do, hold on, I'll write it down. What I'm saying is, and if you're starting to think that we've done this like many times, you're right. I'm trying to show you it's true across the board in nature and technology. This is true. Any differential equation of this form, no matter what the variable is in any harmonic oscillator, no matter what the variable is, what I'm saying is if we happen to know that D, whatever P might be, if we happen to know that we have d2p dt squared equals negative 36p, and I just made up 36 arbitrarily, like maybe it came from a k and an m, or maybe it came from, I don't know where it came from. But if we just know that, and we know that that's the number in there, that it's a positive constant, then we automatically know that the value of P is harmonically oscillating, is obeying a cosine function, and we know that the rate of it, omega, is automatically the square root of that 36. Omega is automatic. Like I don't have to do the math again because we've done it once is the point. So omega, the radian, it will automatically, this thing will automatically oscillate at a rate of 6 radians per second. 6 because 6 is the square root of 36, and why square root? Because when you take one derivative of this P function, the 6 comes out the first time from chain rule. So you get negative 6 P naught sine 6t. And then you take the second derivative and the 6 comes out again. So the 6 ends up getting squared, right? And negative, and so d2p dt squared equals negative 36 times P. It satisfies the equation. So, and that's always going to work like that. So I'm saying, back to this, from now on, the reason we call, so from now on, we call that constant in the differential equation, we call it omega squared, because we know that the square root of it is going to be what omega is. Okay. And omega, omega is that cycling rate that apparently does not in any way depend on P naught or Y naught or A or whatever. So what this means, what's special about a harmonic oscillator is it literally means, again, picture the mass on the spring of homework 1 that we've been talking about forever. Remember that mass on that spring, it had a certain K of 200 newtons per meter. It has a certain mass of 0.3 kilograms. And we pulled it back. We set up our system. We pulled back the mass. We held it at an initial displacement from equilibrium of 15 centimeters, right? Of 0.15 meters. We held it there and then we let it go and it went wah, 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 right? It did so at some certain angular frequency. Actually, we found it out. I think it was like 628 radians per second, I think. I don't know, it doesn't matter. So it's going back and forth at some rate. Wah, 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 right? Fine. It's going back and forth at some constant rate, a constant rate. Very nice. It's constant. Very nice. Okay. Here's how constant it is. If we stop the whole thing and we say, you know what, let's try again. Let's take the same spring, the same mass, but try totally again. And instead of pulling it back to 15 centimeters, let's pull it all the way. Let's pull it to like 55 centimeters. Let's start it way out here and let it go. Well, that'll work. That'll work. We let it go from here. It's now going to go all the way from 55 to 0, all the way to negative 55 on the other side. It's going to make much larger oscillations, right? Okay, no problem. But here's what I'm saying. The omega rate is just the square root of the constant in the differential equation. The omega rate did not in any way depend on X naught. There's no equation that relates omega to X naught. Omega doesn't depend on X naught. So if we pull this thing all the way out to 55 centimeters rather than 15, right? That changes the X naught, but that doesn't change the omega. So evidently, if we pull it all the way out to 55 centimeters, now we're asking it to make a much larger trip. Like it's got to go all the way here and all the way back. But evidently, it's going to do this a lot faster. Evidently, if I pull it all the way out to 55 centimeters, it has a lot more potential energy than the one that was pulled to 15 centimeters. It's got so much more potential energy that it's going to convert to a lot more kinetic energy by the time it gets to the middle. On average, this one way out here will have a lot more kinetic energy than the one over here. So on average, this one is going to go a lot faster on average than the 15 centimeter one. And it's going to go a lot faster by apparently exactly the right amount. By exactly the right amount, so that womps will take exactly the same amount of time as womps. Like literally, that's what I'm saying. I'm saying that if an oscillator is truly oscillating harmonically, it doesn't matter. Sorry, it doesn't matter how you set it up. It doesn't matter how much space you ask it to transverse, to traverse. It doesn't matter how much space you ask it to traverse. It doesn't matter how big of an amplitude you give to its oscillation. Somehow all of its oscillations are going to take the same amount of time. Rate of cycling in time is independent of configuration in space for a harmonic oscillator. This will take 3 seconds, or this will take 3 seconds. That's crazy. That's part of what we're saying here. That is the essence of harmonic oscillation. What I'm really saying, if you're following me, is a harmonic oscillator is a clock. A harmonic oscillator is a true clock. It's a metronome. It is a timekeeper. It's such a good timekeeper that it doesn't even care what's happening in space. It'll keeping the same amount of time. All clocks, all watches, all timekeeping devices use as their fundamental central ingredient some kind of harmonic oscillator, whether it's a mass on a spring or a pendulum on a grandfather clock or a harmonically oscillating electronic circuit in a digital watch. Someone's here. A harmonic oscillator is a timekeeper. Harmonic means that steady, so steady in time that you can't even mess with it by changing its configuration in space. Okay. that's what's really important about omega, which leads you to F, which leads you to T. And omega, what I'm saying in sum about all this, and I know I only have 15 minutes left to get to the other stuff. What I'm saying about omega, oh, good, thank you. She's rocking today. She's making my day, Elizabeth, with an S. I mean, not that it's about me, but no, cool. I'm glad, and I appreciate. And look, even if I appreciate that, Elizabeth. I mean, if nothing else, it shows that she's hearing what I'm saying. Yeah, I mean, yeah. Now I almost want to say more about it, but I won't. But thank you. Yes, that, so harmonic means that steady, and no problem. Thank you. No, I got you. Thank you. No problem. That's to someone else. Director. Okay, so. Okay, I'm going to actually go a step further with this just because one person said it was cool, I guess. Like when I say that clocks are made from harmonic oscillators, I really mean it. And again, you might even be saying, okay, but that's nice in physics land, but what about like reality? Like what about reality? Like what about friction and stuff? Just as a quick thing, like if you, a regular everyday pendulum in real, like, you know, you start it back here and it starts going like this. And then in everyday real life, a pendulum does experience some kind of friction, of course, for sure. I mean, better pendulums experience less friction, but a regular pendulum will experience some friction. So indeed, now, and here's where I'm gonna make the point even stronger, not weaker. Of course, it is true that in reality, a regular everyday pendulum or a regular everyday mass on a spring will experience some friction and therefore will damp a little bit in time. Meaning, if you watch a regular pendulum, sure, its swings will start getting shorter and shorter in length as time passes because there is some friction. So realistically, a pendulum might start off at 18 degrees and then eventually its swings are like 17 degrees and then 16 degrees and then 15, right? So you might look at that pendulum and say, oh, that pendulum's slowing down because it's like a kind of crappy, or you might say that that clock is slowing down because it's kind of a crappy, realistic, frictional clock, right? So it's slow. Look, the swings are getting shorter, so it's slowing down. But hang on. What I'm saying is, oh, sure, the swings might be getting shorter in length. But the fact is, the length of the swing doesn't affect the time of the swing. That's actually what I'm saying. That's what Elizabeth is noting. So I'm saying, even in reality, I'm talking about reality now. You know, that place that we sometimes visit? Reality. Even a realistic frictional pendulum will demonstrate shorter and shorter arc lengths. So when you look at it, you might go, oh, that pendulum's slowing down. The clock is slowing down. It's not that good. But actually, you're so right that you're wrong. Not you, someone to say that. They're so right that they're wrong because while the swings are getting shorter and shorter, it actually is slowing down. It's actually slowing down. Like each swing has less potential energy and less kinetic energy. So each swing is actually slower on average in the traditional sense of speed. Therefore, and to the point where the shorter and shorter swings are taking the same amount of time as the longer and longer swings. So even a realistic pendulum, as it damps out, as it appears to be slowing down and losing time, it is slowing down, so it's not losing time. It's just losing space. That's why a freaking pendulum is a clock. I'm not saying anything is perfect in life, but I'm saying even crappy pendulums are a heck of a lot better than you actually think when you look at them. They're keeping time even while they don't keep the space. Who first discovered this? Galileo, when he was sitting in church, sitting in the Sistine Chapel, looking up at the chandeliers, swinging back and forth. And he was like, oh my God. I mean, I think literally he was like, oh my God, that's cool. But this is for real. Like he's looking at them and he's noticing, just like all normal people notice, that they're going shorter and shorter. So it looks like, oh, you know, but then he's like, wait a second. Even that thing's getting shorter. I think that thing is keeping time. And he tested it and he's like, that thing is keeping such good time that I think I can invent a freaking clock out of it. And like, there weren't really good clocks before then. There weren't mechanical clocks, but there were like sand glasses. I mean, what do you call hourglasses, which are okay, but not great. And he was at the forefront of inventing the first mechanical, reliable clocks. They were so reliable that then he started doing physics with them. Like he invented time keeping devices that were reliable enough that he could then start sliding things down ramps and doing like labs in his lab, in his house. He could start like rolling things down labs and measuring the down ramps of various inclines accurately enough that he could extrapolate from these various inclines the rate, the 9.8 number that we all use today. He figured out that constant 9.8 number by slowing down things on ramps and timing them with timers that he made based on his recognition that clocks actually can be made and actually exist because harmonic oscillation exists in the world. Like he made clocks good enough to do physics from because he understood physics. I mean, how crazy is that? And now I'm going crazy, but it excites me every time I think about it. Like, and it's almost circular, right? Like he figured out enough physics to realize that there are physics devices that keep time. And then he used those to keep time to do physics. Want to know something even crazier? You might be thinking, if you're hearing me yell about this, you might even be thinking, wait. You might be thinking, wait. He looked at the chandeliers in the Sistine, and this is true, by the way. Maybe it's not, but it is. If you know, like this is not like the story of Newton sitting under the tree and the apple fall. No one thinks that's true. This is real. He's sitting in church watching the and we know it's real because we have the evidence, like the equipment that he used. But anyway, he's sitting in church looking at the things going like this and going, oh my God, I think that thing is actually always taking like 2 seconds to go back and forth, even when the swings are getting shorter. So he's like, I think that's always taking roughly the same amount of time. Could I be right? Let me test that. And so he tested it and he was, nothing is exact, but he was right enough to do stuff with it. You might be thinking, if you're really listening to me, you might be thinking, well, wait a minute, if they didn't have clocks, you see where I'm going with this? If they didn't have clocks, which they didn't, I mean, they had hourglasses, they had things, but they did not have mechanical clocks. They did not have reliable clocks. They did not have clocks that were good enough to be used at sea, by the way, which was like a very, very big problem, which Galileo helped solve in more ways than one, but they didn't really have clocks. And when I say they, I'm talking like Galileo died in 1642. He was born, I think, in 1582. I'm talking about like the late 16th century, early 17th century. They didn't have clocks. Galileo's sitting there and basically discovers the first possible mechanical clock because he discovers it's taking the same amount. He discovers a harmonic oscillator, taking the same amount of time to go back and forth regardless of space. And he's pretty sure, he's like, oh, I think that's keeping the same amount of time all the time. Let me test that. Now, if you're really paying attention to me, you might be thinking, I'm actually just going to check in the chat. Like, and I'll even give you a moment. Like, what's weird about what I'm saying? Like, there is a slight problem in what I'm saying. Like, I'm saying they didn't have clocks. He's sort of discovering something that might be a clock. He's going, I think it keeps time, but I'm not sure. Let me test. Oh, I tested. Oh, it is keeping good time. Does anybody see what's weird about that? Like, there's something missing that I'm not mentioning. Like, how did he, like, do you see how that's a little bit weird? That, yeah, exactly. Elizabeth, she's on total fire. This is like the Elizabeth channel today. Yeah, like, let me just say, and again, maybe I'm going off on a little tear here. I know we have to get back to material, but this is just like, this is what physics is about, really. Yeah, I'm telling you all that, right, not only units, not even just units. And this brings you back to, oh, if you ever did lab 1, but you had COVID. I don't know if you ever did lab 1 in physics 203. But yeah, like what Elizabeth and Maisha are getting at, it's even more basic than what they're, like Maisha saying, how did he choose units or increments? Like, how did he even choose any, like, yeah, how did, if he's looking at this thing going back and forth and going, I think it's taking the same amount of time to do each swing. The question, and then he's like, let me figure it out. Let me test. Oh, yes, it is. What did he use to test? I mean, this is what Maisha and Elizabeth are saying. Like, if he's looking at something thinking, I think that might be a clock. I think that might be something we can use to measure time, but I'm not sure if it's keeping really good time. What the heck did he use to compare that to know whether it was keeping time or not? You see what I'm saying, right? Like, that's great, but there is an answer. And you see the question, right? Well, I'm just going to assume you do. But the answer is he used his heartbeat. Right. Now, look, I don't even know what you think. I mean, I'm pausing because like, it actually gives me shivers to think about that. Like, yeah, he used his heart, exactly. And y'all, if I may, like, that's such a important point, because because first of all, like, I don't know, it's just so spiritually uplifting to think of that it all comes back, like, all of physics in the end is either coming from way outer space, the heavens, or it's coming from right inside the body and the soul. Like, physics, it is in heaven as it is on earth, is the lesson of physics. Like, it's all either coming from way out there or it's coming from directly in here. But all the stuff we understand in between is coming from one place or the other. But here's the thing, like, he used his heart. And what you might say correctly, of course, is, wait a minute, he used his heart? Is that a perfect clock? How perfect is his heart? And also, what if he was getting excited? He probably was getting excited. How good of a clock is his heart? Here's the answer. Of course, it's not perfect, but it's good enough to work. And when I say work, what I mean is it produced all these results. Like, we can sit here and say, your heart's not that great of a clock, but evidently it was great enough for him to believe his conjecture, it was good enough for him to trust his conjecture about the chandeliers, which was good enough for him to then go back and build pendulum clocks that were also not perfect, but good enough to lead him to the inclined planes and to experiments that got him to 9.8, which was not perfect, but good enough to get us to a larger sense of capital G and G equals M, F equals GMM over R squared, and eventually get us to the moon. What I'm saying is, this is the thing about science, is it's never about perfection. It's about results. It's about, if it freaking works, that retroactively proves that something was right somewhere. If it gets you the results, the reproducible results in the real world, you're doing something right. And if you stop and wait for perfection, you will not move forward, right? Perfection is the enemy of the good. And the good is the enemy of the great, right? You see, well, yeah. Oh, that's nice. Yeah, totally. Yes. I mean, it kind of is in science. Like, science is not what it looks like to the outside world. Science is art, right? I mean, or it's heart or whatever. Like, but it has a result at the end of the day. Yeah, no, that is awesome. That, even that we did, yeah, and yeah, that is totally Elizabeth. I almost want to just end the class on what Elizabeth just said, and the fact that Maisha just gave you credit. And I pretty much will. There was more that I actually did want to deal with today, but I feel like it's going to corrupt this point. Like, and let me tell you all that this is really a point to you also about homework and exams and forensic science major and all that. Like, really, science is always presented to all of us, like from the textbooks and the overhead projectors and the PowerPoints. It's presented to us like this. It's presented after it's been cleaned up. What's presented to us from science is these fabulous results that are so clean and shiny and sort of motivating, but also cripplingly scary, right? What's presented to us from science motivates a lot of us to try, but it also just crushes our egos and our spirits when we don't reach that level that seems to be presented in the textbooks and on the overheads and everything. The truth of the matter is that science is not about perfection. It is a messy, messy process that is about moving forward. It's about 2 steps forward, 1 step back. It is about experimentation. It is about actually being willing to be wrong in private and in public for the sake of forward progress. And forward progress is measured, literally measured by external results, right? So those of you who get how you're not going to do the homework perfectly the first time, or you're not even going to do an exam perfectly the first time, but you're just going to keep the beat going, and you're just going to keep handing things in and just keep revising and just stay with the program. And those of you who know that you are destined at least once in your science major to have a moment of crisis where you're like, oh my God, I don't know if I belong here. Oh my God, I don't know if I can keep going. Oh my God, I'm actually getting B's and C's. I never got B's and C's in high school, let alone D's or whatever. Like, or oh my God, maybe this was a big mistake. Or oh my God, and I don't mean to keep saying God, but like, or oh my quark, like, wait, I could do this. I guess I could survive and hang on this crazy major, but in order to do it, I never get a weekend again. I never get friends again. I just sit here and suffer while everybody else in some other major in the college is like whooping it up every weekend, like with beers and no masks. Like, is this really worth it? My answer is yes. My answer is you do belong here. If you've gotten this far, you do belong here. And especially if you have a moment of crisis where you're asking yourself, do I belong? Yes, because everybody who sticks with this and who is here has that moment of crisis. And some people admit it and some people don't. But nobody gets through this stuff without a moment of crisis and asking, can I really handle this? And nobody handles it as well as they make it look like 40 years after the fact or in a textbook or blah, blah, blah. Nobody, including Galileo, nobody just nails this stuff. Everybody farts around and has crises and mistakes and MSRC support systems and everything. And the difference between the people that make it in science and get jobs and all that, and the people that don't, is that the people that make it kept going even when they didn't think they could make it. That's the difference, like honestly. So just keep going, especially when you don't want to, but no problem. But I do mean it, and I really mean it. And I mean it as from both sides of the situation. But okay, so there was other stuff we were going to do, but I'm not going to do it now. I think that is a more inspiring note to end on. We will get to it, but it will be in the notes. I'm going to put the notes in your thing. So if you want, you can look at it to see what I would have explained anyway. But I will, and you didn't miss anything. Like everything I explained is perfectly adequate for the homework. I promise you that. So, okay. Thank you guys. And thank you very much for your participation today. It was awesome. So I'm going to go. Have a great weekend. Thank you guys. Awesome job. Awesome. Thank you. Bye.